Hello everyone, we are grouped Diamond 3. Here, we will show you the design of our agents.
Before we consider the different techniques with which we want to experiment, it's important to consider the characteristics of the problem at hand. So this is because no one-size-fits-all AI technique exists. A given approach may excel at solving one problem, but be terrible at solving another. So we first identify the characteristics of a Zuo. Firstly, the actions within a round are deterministic. This means that in a given game state S, action A will always result in the same successive state S prime if S and S prime belong to the same round. However, the game state at the beginning of a round is stochastic. So while actions within a round are deterministic, the state S0K, the initial state of round K, is stochastic and it isn't determined by the state in the previous round. This is due to the randomized draw of tiles from the bag. Thirdly, the problem is adversarial. The goal of the problem is to both maximize the agent's score and win the game. That is, end with a higher score than the opponent. So our goal is in tension with the opponent's goal. Lastly, there's perfect information. The entire game state is visible to all players. This brings us to the techniques that we tried.
So let's talk about the algorithm we think it will work for our system. First, Monte Carlo tree search is a probabilistic and heuristic driven search algorithm that combines the classical tree search implementation alongside machine learning principles of reinforcement learning. There is a problem with a large state space. MCTS does not need to consider the whole state space and only focus search times in more relevant parts of the tree and visits more interesting nodes more often. In each turn of the draw, we are only given 1 second to make the decision. And MCTS is an anytime algorithm, so it is possible to stop the algorithm at any given time to return the current best estimate, which is suitable for this problem. Also, MCTS can operate efficiently without any knowledge in the particular domain, apart from the rules and the end conditions. We also use Minimax to implement our agent. When we were improving our MCTS, we found out that we cannot get enough iteration within the time limit. Since we can control the depth and reduce the number of nodes in the game tree by using alpha-beta pruning, we may be able to do more analysis by using Minimax decision theory.
TD, like MCTS, can learn without an MDP model, relying on simulations instead. However, unlike MCTS, TD methods do not wait until the final outcome is known before updating estimates. We predicted that TD learning may provide our agent with an edge over our MCTS agent due to its bootstrapping characteristic borrowed from DP. We figured perhaps it might learn more quickly than MCTS. The principle, elegantly explained by Sutton and Barto's analogy of driving home on the highway and being able to update the live prediction on the way, was thought to be highly applicable to Azul as well.
The design of our best agent is based on Monte Carlo tree search. In our MCTS, we do self-chaining. We not only propagate our rewards, but also the opponents. Each node in the tree would update their Q values based on their own ID. The opponent nodes would select their move based on their own Q value. There are two main challenges in this game. The first challenge is that we cannot do enough iteration within the time limit. The reliability of MCTS depends on the number of iterations. To improve the iteration process, we come up with many strategies. First, we use some domain knowledge to filter out unlikely move before expanding. We also process our rollouts that are more similar to the one that would occur between human opponents. This is because we cannot get enough rollouts to get an accurate estimation if we use random choices. The second challenge is that it is hard to estimate the rewards you get in the current round. For example, the unfinished pattern may hinder you from getting a good score in the next round. In addition to get the scores of the current round, we also use some domain knowledge to provide future scores estimation. Even though our MCTS player is better, however, given additional times and resources, we would have liked to see how our TD agent would improve after having the chance to train extensively over a broad range of opponents in order to truly refine the rates. Perhaps that is after training extensively against other teams' players. Because our TD agent didn't get enough training, so here I will only show you guys our TD agent didn't get enough training. Here I will only show you guys our best player versus our Minimax player. This one is our best player and this one is our Minimax player. And you can see here the Minimax player put a tile, just one tile into its fifth line, which is not supposed to do this. Why this would happen? It is because the Minimax player can't get enough analyze when there's many moves, when there's start of the beginning. So you can see most of the times the depth is 0. Why? Because if it increases the depth, the iteration will be very huge, and that is what we can't handle in just 1 second.